Okay. So we're going to start with spectroscopy again today, spectrometry. The topic we're going to talk about, we're going to take this in 2 weeks, is mass spectrometry. And this week I'm going to talk about the basics of it, and then next week we'll talk more about some fragmentation patterns and how those occur. And next week there'll be a small homework assignment for the spectrometry. But this week is just going to be kind of a overview of what it looks like. So mass spectrometry is not a spectroscopy technique. So there's no ground state excited states to worry about. There's no absorption of any kind of radiation. Instead, it's a technique where we determine the molecular weights or the molecular mass of an organic molecule, and we can also use it to determine the identities. So in a basic mass spectrometry experiment, you take a molecule and you have to get it into the gas phase. Now, for simple organic molecules, we might just stick it in a GC. For things like proteins and other biomolecules, that's not trivial to get a big molecule into the gas phase, but it can be done. And the people that finally did get mass spectra on things like proteins won the Nobel Prize, and now it's used all the time for sequencing and other things. So we need to get the molecule into the gas phase. Then once we get it into the gas phase, the molecules get hit by an electron beam. So there's just a beam of electrons that flows basically perpendicular to where the molecules are flowing, and by collision, the molecule loses an electron. So just the collision of one electron with the molecule kicks out another electron. And what that does is that leaves the molecule then with a positive charge. And also, because most molecules come with an even number of electrons, if they lose that electron, they basically become a radical. And so this is called a radical cation. And those are the species that we deal with most in mass spectrometry, is the idea of this radical cation. But the radical cation may or may not be really stable. And so it may break apart in a process that's called fragmentation. And ultimately, we're going to measure the masses and the abundances of each of those masses in the mass spectrometer. So in terms of what a mass spectrometer looks like, and this is an older version because there's different types now. We take the sample and we heat it into the gas phase. And then this whole system is under vacuum, because if you're going to have gas phase molecules, you can't have them colliding with oxygen or nitrogen or carbon dioxide, and so the system has to be under a very high vacuum to keep the molecules collision free. The molecules come into the system, they're hit by the electron gun. Basically, the electron gun or the electron source is just a filament, like in an incandescent light bulb. Only under high vacuum, when you heat it, it shoots electrons out. And if you have a positively charged plate over here, that forces the electrons to move in a straight line. They occasionally collide with a molecule, and when they do, we make the cations, the radical cations. So then you have some negatively charged plates here to pull the positive charges towards them. There's a small hole or a slit, and the molecules that strike the side of the plate don't go into the mass spectrometer. Those that do go in through a really small hole, so they go in a straight line. And there's a couple more negatively charged plates here to kind of move them into the system. Once they move into the system, then they come into a magnetic field. Now, the basic physics is anything with a charge that moves has a magnetic field, and therefore can be moved by a magnetic field. So if you have radical cations moving, you can take a magnetic field and you can make them move. You can make them turn corners, you can make them smash into the sides of things. And so what happens is that by setting the approximate or the appropriate magnetic field here, you can take the radical cations and you can make them do a 90-degree turn and come down here and strike the detector. Those molecules that don't fit that magnetic field, the ones that are too light get attracted too much and they crash here. Those that are too heavy never quite make the turn and they crash there. So the idea is that if we take that magnetic field and we scan it, we can basically choose masses and run through the sequence. We could go 98, 99, 100, and have each set of molecules then pass through and get to the detector. So in the end, what we do is we plot what's called the abundance down here. We plot the abundance of the peaks versus their mass to charge ratio. Okay, and so we get a mass spectrum. So where we see these peaks, well, those are molecules with a mass of whatever, maybe 35, 59, something like that. And then the height of the peak is the abundance, how many ions struck the plate or struck the detector for that particular mass. And so that gives us then a mass spectrum. Now, it's a mass to charge ratio. And for the most part, for organic molecules, the charge is +1. So if the charge is +1, then that means we can just read the masses directly off of the mass spectrum. Now for proteins and other biomolecules, they sometimes have charges of +2 or +3. Then it's not so simple. But in this case, since most of the molecules we work with are +1, we can just read the mass of that particular ion. And the key thing is that in order for this type of a system to work, you have to have a charge. The only way the magnetic field will bend you is if you have some sort of charge. So if you're a neutral molecule, you're just going to smash into the sides. Okay. So those are the basic principles for the mass spectrometry. And so we make the ions and then we analyze how many of each mass of the ions there are. Okay. Now what we do most of the time in organic is to couple mass spectrometry with gas chromatography. So you get gas chromatography and mass spectrometry, which is GCMS. And you hear this all the time on the forensic shows. They're using GCMS constantly, along with DNA. You know, you'd think that's all there is in a crime lab is a GCMS and some magic machine that gets you a DNA profile in 5 minutes. But what we do is we inject the sample into the gas chromatograph, the compounds separate on the column, and then each column sequentially as it comes out goes into a mass spectrometer so we can get a mass spectrum of every compound that comes out in the mixture. And so we can identify each component. For proteins and other things, we don't do gas chromatography. We just inject the sample directly. There is liquid chromatography that can be used for molecules that don't go into the gas phase. But we have 2 of these instruments, 2 gas chromatic GCMSs. One's not working right now. If you walk by the instrument room, you'll see this one. This is the one that is, and it's like a year-ish old. And it's basically one that the coroner's office has, that the drinking water plant has, and a lot of other places. What you have is you've got the GC part here, you've got the mass spectrometer part there, and then there's a tray on top that has the little robot that sucks the solution up and injects it. And just like on TV, sort of. Except on TV they get their results, spit it out in about 2 minutes. And in real life it's not that simple. Okay. And so on the inside of the GC there's a column that looks very similar to the columns that you used on the GCs if you did gas chromatography with Faith. And so we have the components separate, and then the mass spectrometer analyzes each component that comes out. So what we get is something that looks like this. We have a gas chromatograph part. Each one of these peaks represents a different molecule in this mixture. This is a mixture of an essential oil called lavandin. Essential oils are what are used to make colognes and perfumes. So this particular sample has a lot of different organic molecules in it. And then for each peak, for each molecule, we can get its mass spectrum. And notice in the mass spectrum what we have is we have sort of a scale of abundance. Mass spectra peaks are just lines. It kind of looks like a bar graph. And then this tells us what ions have come out for that sample. And as we go through this, I'll give you the basics. But for the most part, this molecule that came out has a molecular weight of 154 atomic mass units. And then that ion is not stable, and so it breaks up into individual parts, and each one of these lower masses then is a part of that molecule. And so you can take those parts and try and put them back together to figure out what the overall molecule is. But what we're going to talk about initially is getting the molecular weight from the molecule, and then what's typically done is to use this set of peaks as a fingerprint for the molecule. And so this idea that there are different masses of different heights gives you a mathematical sort of fingerprint for the molecule that can be searched in a database to try and figure out what is close to it. So on CSI, they'll take some sample and they'll inject it, and they'll come back 2 minutes later and they'll say, oh, this sample was made up of this, 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 and this. That's actually real. That's not made up. The 2-minute part is made up when it takes that long. But what you do is you just take this mass spectrum and you match it in a library against known compounds, and it'll give you a list of what the most likely compound is. And in a forensic setting, they've already run authentic samples of the known compounds they're interested in. So they know that cocaine comes out at 8.7 minutes. So if they get a peak at 8.7 minutes and its mass spectrum matches up with cocaine, it's cocaine. Or anything else, any other sample. So that can be done. You can actually narrow down the list of components by just computer matching the mass spectrum. If the compound's never been made before, then obviously it's not going to be in the database, and so there's going to be no match for it. But that's the only real limitation. Okay. So this is what we see, a gas chromatograph, and then for each gas chromatograph, a mass spectrum. Now, in terms of mass spectrometry then, it gives us several things. Number one, the molecular weight of the sample can usually be determined. And we can determine that from a very, very small amount of sample. Okay, mass spectrometry, GCMS, is used in drug testing. Okay, so if you had to take a urine specimen and have it drug tested, it was drug tested most likely by GCMS. What they're doing is they're looking for metabolites from your system that occur when you take whatever illicit drug or steroid or whatever it is. You're going to get certain metabolites that come out, and that's what they're analyzing for. You know, like they're going to be doing, I would imagine, Michael Phelps's really soon. He's probably going to have a drug test. Only his will probably be a hair test to figure out exactly when he was, you know, if he inhaled. That would have been the best line, but I didn't inhale. Nobody remembers that from the last person who said I didn't inhale. No, nobody does. So anyway, we'll just move on. No, it was a former president. So that's how it's used, but those metabolites are in really small concentrations. And so you can look at sometimes nanograms of materials to milligrams. So it doesn't take a lot of material to get a mass spectrum or a GC mass spectrum. And so what we can do is once we determine the molecular weight of the sample, then we can determine possible molecular formulas for that compound. And if you've talked about degrees of unsaturation, then you can calculate the degree of unsaturation for that molecule. That's how many rings or double bonds or combination of the two are in the molecule. And then the computer matching aspect of it is that you can use the masses of the fragments and how high they are as a way to search and basically match up the fingerprints of the molecules so you can identify or at least narrow down the possibility of that molecule's identity. So if there's 9 million organic molecules and you can narrow it down to like 20, that's pretty good. Of course, the limiting factor is it had to have been made before and it had to have been run before. If not, then this doesn't help you. Okay. So here's a mass spectrum, and what happens? Well, if you take this mass spectrum, here's one, the simplest one of methane, CH4. So when the methane molecule gets hit with the electrons, it forms the methane radical cation. Now that's what we call the M dot plus peak, which is called the molecular ion. And that's what we will call this molecule's molecular ion. And the molecular ion is basically the intact molecule before it's fragmented and fallen apart. So methane then has a carbon and 4 hydrogens, so its molecular weight would be 16. And so what you see is, you see that the CH4 dot plus occurs with a molecular weight of 16. Okay? If I didn't know that this was methane, I'd know that that molecule had to weigh 16 AMUs. But then what about these fragment peaks? What about these peaks that occur at less than 15 or less than 16 AMUs? What happens? Well, what happens is that the CH4 dot is somewhat stable, but it can lose a hydrogen atom. We can break a hydrogen atom off of this, and that would leave us with a CH3 plus. Okay, so if you took a CH4 dot plus and subtracted an H dot from it, you get CH3 plus. Well, how much does CH3 plus weigh? Well, it's 12 plus 3 is 15. And so this peak at 15 corresponds to basically the methyl cation, the methyl carbocation. And now before anybody gets all excited and said, now wait, in lecture, if we wrote a methyl carbocation, you would take points off, which is true. Do they exist? Well, in solution, primary and methyl carbocations don't exist all that much. But we're dealing in the gas phase. And so in the gas phase, primary carbocations and methyl carbocations are perfectly fine. And they have to be perfectly fine because I see a peak right here due to that. Okay, so the methane will break apart and lose a hydrogen atom. Now, why don't I see anything for the hydrogen atom? Because it doesn't have a charge. And so once the hydrogen atom gets formed, it just crashes into the side. No charge, no ability to make it bend. Then you can see that there's peaks at 14 and 13. Well, if I take this CH3 plus and I subtract off another hydrogen atom from it, I'm going to end up with a CH2 dot plus. Well, what's the CH2 dot plus weigh? 14, 12 plus 2. And so this is your CH2 dot plus. And then looking at 13 and 14, or 12 and 13, 12 would just be a carbon atom with a positive charge, and 13 would be a CH. But notice that in terms of the abundances, we don't form very much CH2 plus, and we form mostly CH4 and CH3. Okay, so every time the molecule fragments, it's actually less likely to do that, so those peaks may get smaller over time. What? I'm going to get to 17. I'll get to what 17 is in a minute. Or two. Okay. So if you take a big molecule, there's lots of ways the molecule can fragment. And that pattern then can tell you about the structure if you analyze it in depth. But it can also give you that fingerprint that you can use. Okay? But here's the key. The key is that every one of those masses that shows up came from an ion. Okay, so if you have a neutral molecule that weighs 14, you would never see that because it would never get bent by the magnetic field. So if we look at a couple of alkanes, nonane and 3-methylpentane, these are their real mass spectra. And when we look at a mass spectrum, what we try and do is we try and find the peak that's all the way to the right. Okay, the peak that's all the way to the right is the M dot plus peak, and that gives us the molecular weight of the molecule. So for nonane, nonane weighs 128, and 3-methylpentane weighs 86. Okay, that's its molecular weight. Now notice that in both of these cases, those molecular ions are really small, which means that once they're formed, they begin to fragment apart. And it turns out that the fragments are more abundant than the molecular ion. And so that's why it's sometimes a little difficult to get molecular weight, is that if your molecular ion is so small you can't see it, then it becomes a little bit more difficult to see. Well, if we looked at this, we could actually think about how we get some of these other fragments. And I'm going to talk more in detail about how we get them next week. But let's take a look at the 3-methylpentane. If its molecular weight is 86, there's a peak at 71. Well, how did I get from 86 to 71? I lost 15 atomic mass units. Well, what weighs 15 atomic mass units? A carbon and 3 hydrogens. So how did I get to 71? Well, 71 was when this molecule basically broke a carbon-carbon bond and lost a methyl group. So the fact that I see a mass peak where I lost a mass of 15 tells me, hey, this molecule has to have a methyl group in it. And we can even go farther than that, because we can look at it losing an ethyl group, which would be 2 carbons and 5 hydrogens. So sometimes we look at the peak itself and say, well, what part of this molecule would this mass represent? But sometimes we look at it to say, okay, 86 minus 59, what's that? Well, that's 29. And so 29 is a C2H5, and that's an ethyl group. That's this 2 carbons, 2 hydrogens, 3 hydrogens. You break that bond, and you would form that fragment. Okay. So the fragmentations, the fragments themselves can tell you about the structure. We are not going to give mass spec nearly its due here, but if you wanted to, you could figure out the structure of a molecule from its mass spectrum. You can do a pretty good job of that by looking at what fragments were lost and what fragments exist. But we'll talk more about that next week. Here's the key thing, though. The peak that's farthest to the right is the molecular weight. Okay, that's the important part. So if you have the molecular weight, what can you do with it? Well, if you have the molecular weight of the molecule, there's only a certain amount or certain number of formula that add up to that particular molecular weight. So for instance, if you had something that weighed 154, here are all of the possible molecular formula that weigh at 154. And so I can narrow down my list. You'll see in this case there's a lot of nitrogens, oxygens. If I knew my molecule had no nitrogen in it, then I could eliminate probably most of those from the list. If I knew how many carbons were in my molecule, I could narrow down that list a lot as well. Now, if I had a mass spectrometer that was able to get me the molecular ions peak to 3 decimal points, which is called exact mass spectrometry or high resolution mass spectrometry, I could actually narrow down to exactly what molecular formula is, because all of those molecular weights vary to the 3rd decimal point. And so a lot of times if we do a high resolution experiment, I can look at that list and say, it's got to be this in terms of its molecular formula. So the molecular weight can tell you an awful lot. Once you have a molecular formula, we talked a little bit about this in my lecture class, you have degrees of unsaturation, and so you can figure out how many rings or double bonds are in the molecule. And if you couple this with something like infrared, and you know you got a benzene ring, well, you'll know how many minimum carbons you have. So the molecular weight can give you the molecular formula, which is important. And it could also then be used to computer match. Now, young Eli asked what the peak at 17 was, which is a good question. I said that the peak the farthest to the right was the molecular ion peak, but I ignored that little teeny tiny peak at 17. Well, in mass spectrometry, we have to take into account what are called isotopes. And this peak at 17 corresponds to a methane dot plus that isn't made up of carbon-12. It's made up of the isotope of carbon that weighs 13 AMUs. And so that peak is actually what is called our M plus 1 peak. Now, as I'll show you in a moment, carbon has 3 different isotopes. Basically, the carbon-12 isotope that weighs 12 is 98.9% abundance. Carbon-13 has 1.1% abundance, and the carbon-14 that's used in radioactive dating is less than 1%. It's a trace amount. So what that means then is if I had 100 methane molecules, one of them would have a carbon-13 in it, and the other 99 would have carbon-12s. And if I made the sample big enough, eventually I'd find one carbon-14. Okay. So this peak at 17 is that one molecule in 100 that weighs 13. And so the 13 plus the 4 gives you 17. And where this becomes important is that if you think that every carbon in the molecule has a 1.1% chance of being carbon-13, then what happens is that if you measured the intensity of the M plus 1 peak relative to the M peak and divided by 1.1, you would end up with the number of carbons in the molecule. So if you had 10 carbons in your molecule, that means the M plus 1 peak should be 10% of the M peak. So that just simply by doing that experiment, you can say, I have 10 carbons in my molecule, or I have 20 carbons in my molecule, or I have 5 carbons in my molecule. Okay, that's another piece to the puzzle to try and figure out what the identity is. We don't use that very much anymore, but it still can be used. So you'll see these isotope peaks, or you'll see the M plus 1 peaks. And so they can tell you about the numbers of carbons. That's an important aspect that could be used. It was more important in the older days than it is now. Now the other thing that happens is that if you have a chlorine or a bromine, if you have a halogen in your molecule, it will stand out. Because if you look at the different isotope ratios of different molecules, for chlorine, for instance, there's a chlorine 35 and a chlorine 37 that's 75 and 25% abundant. Bromine has a 50-50 or nearly 50-50. It's a 51-49 ratio. And so if you have a halogen on your molecule, you're going to see two mass peaks. Because one of the mass peaks is going to be corresponding to the bromine with a mass of 79, and the other one's going to be with the bromine of 81. And so you don't see a single mass peak, you see a double one. If you have chlorine, you have a double one, but they're not 50-50 now, they're 75-25. So for instance, if I have the mass spectrum of bromobenzene, notice that there are two peaks there. One corresponds to the bromine 79 being in the molecule, and the other one corresponds to a bromine 81 being there. And since there's a 51-49 ratio of those two isotopes, those peaks are almost 50-50. Okay. So you have two peaks. Somebody asked on Tuesday, well, what are these little tiny peaks that are next to the two big ones? Those are the carbon-13 M+1s off of those bromines. So each one has a peak 1 mass unit away that's due to the carbon-13 isotopes. Because that 156, the peak next to it is at 158. Okay. And you can actually count the number of bromines in your molecule. If you have two bromines, you end up with what looks like three peaks. Because you've got the possibility of them both being 79, or the two bromines being 179, 181, or two 81s. And so you end up with three possible mass peaks. So if you're trying to determine if you just added a single bromine to your molecule, like if you were doing free radical bromination, and you wanted to make sure you did a monobromination, take a mass spec of it, and you can tell. You can tell what peaks are single bromines and what peaks have multiple bromines on them. You can do the same thing for chlorine as well, only notice in the chlorine case, you've got the two mass peaks, but now they're 75-25 because that's the way the isotope ratios of chlorine are. So at the drinking water plant, they sterilize the water most likely by using chlorine, most likely bubbling chlorine gas into the waters. Well, the chlorine oxidizes the organisms, it kills them, but it also, for some organic molecules, it chlorinates them. And so at the drinking water plant, they have to analyze the water sample for what are called chloro-organics or bromo-organics. And so they look at the mass spectrum to see whether they've got a chlorine or a bromine in there. And too high a concentration is not good in drinking water. So they constantly have to test the drinking water to make sure that these chlorinated and brominated organics are not in the drinking water and measure their concentration. You can see in the bottom spectrum for an iodine doesn't have different isotopes, so it's a little bit, it just has a single peak. Okay. And there are other ones that are important. It turns out that one of the ones that we see a lot that we don't like to see in a mass spectrum are silicon, because silicon has a whole bunch of isotopes that have pretty high abundances. So when we have silicon molecules in our sample, we actually see a large peak and then we see a number of smaller peaks behind it. And that becomes important because let's say that you wanted to analyze a sample, and this is, I think, one of Dr. Miller's beer samples. She studies oxidation, and so she wanted to see if you could see the oxidation of a beer sample by heating it up to 60 degrees overnight and seeing whether the oxidation products could be seen in the vapor phase above that. And she got all these little peaks in her GC, but when we looked at them, and where the little flag is this mass spectrum, we got a compound that had all these isotope peaks after it, which means it was a silicon compound, which wasn't in the beer. It was coming off of the column, because as the column heats up and cools down, it degrades and shoots silicon compounds out. Plus we have little rubber septum that the syringe goes through that are also made of silicon, and so those degrade over time. So in the end, all the peaks that were on top except one turned out to be not from the beer. It turned out to be from the column. And I could go through here and look and say, oh, well, that's a silicon compound, so it's not part of the beer. Okay. So these isotopes come into play a lot. And the important one for us is the carbon-13 isotope, the fact that that M+1 peak is going to be 1.1%, the number of carbons of the mass peak. Right. So where mass spectrometry is used in kind of in a structural sense is that it is possible to be given an unknown compound and try and figure out what it is just from the mass spec. As I said, that part of CSI is real. Now, you just can't stick the stuff in the instrument, oh, it's this compound, and trust it. In a legal setting, they've done all of the standards, and they know exactly where all of the illicit drugs and everything they're looking for show up on their chromatogram and what their real mass spectra look like. But you can narrow down the list. So, for instance, this isn't lavender, it's lavandin. There is a difference between those two essential oils, and I'm not going to get into that because I know way too much about that than I should. But again, there's your GC on top and your mass spectrum on the bottom. I could go through, and given enough time and patience, I could determine the structure of every one of those peaks in that sample. The peak with the flag right now is that mass spectrum. So when I look at this mass spectrum, the first thing it tells me is this thing weighs 154 atomic mass units. And if I looked at the M+1 peak as a percentage of that, I could figure out how many carbons are in it. But without doing that, I can simply ask the computer, okay, go ahead and match that mass spectrum against my library of a couple 100,000 compounds and tell me what the mass spectrum most closely resembles. And when I do that, what you see is the first six hits are all this molecule called eucalyptol, which eucalyptol is a component that is in eucalyptus oil, and it's in a bunch of these other oils. You know, if you take a eucalyptus crop, you're going to have eucalyptol in it. Well, you could say, why did it give it to you 6 times? Well, these databases are constructed so that 6 different people gave 6 different samples of eucalyptol to the database. So the simple fact is when I get to all 6 being the same, I'm pretty sure that's what it is, because these samples all came from different places. And the matches here, this top one was an 82% match, an 80% match, down to like a 77% or 77% match. So I'm pretty sure that this molecule is eucalyptol. Now, if I wanted to be absolutely sure, I would get an authentic sample of eucalyptol and make sure that its GC retention time was exactly the same as this one, and then make sure its mass spec matched up. But if I'm not somewhat interested in that, then I can just simply say, oh, okay, this thing's made of eucalyptol. That's one of the components. Now, if I wanted to know how much eucalyptol was in there, I could create a calibration curve and do all of that. If I want to know what the structure of eucalyptol is, in the newer computer system, I can just say, give me the structure, and it'll give me the structure. Which this is a different, it's got fused rings in it, which is mostly the case for terpenes and other things that make up fragrances. And so that's pretty much par for the course. If I wanted to know where it's found, I could find out where it's found, because there's another button that I can push, and it'll give me all the references. It'll tell me what places it's been found, what papers have been published on it. I might find a paper that says, determination of essential oils in some weird plant. Well, I would know that eucalyptol was part of that. And so I can take a molecule or take a mixture apart relatively quickly. I mean, most of this is pretty straightforward. Somebody gave Dr. Weiner last year a small sample of what looked like an amber, like a amber resin, or he didn't know what it was. He wouldn't tell me where it came from. It was like super secret until we were done with it. So we dissolved it up, we put it in the mass spectrometer, and it came back, and we started looking at some of the components that came out, and they were components that were in resins, and were in varnishes, and were in wood products, like if you used a wood polish, and pine things. And so then I'm like, okay, you got to tell me where the sample's coming from. And it turned out that they had found a small drop of something coming off of a cross in a church downtown, and the priest had taken a small piece of it and had given it to somebody who then gave it to him. And I'm like, they thought it was blood or something? He's like, well, they just wanted to make sure that, they just didn't know what it was. And so what we found was that it was basically sap that kind of came out from the wood, and also the varnish they had used to seal the cross, and so there wasn't anything immaculate going on or anything like that. But he wouldn't tell me that ahead of time, so it was like, okay, we don't really need the secrecy, but you could pick that apart by looking at the different components that were in there and saying, oh yeah, they're all consistent with an older varnish that had been made. So that's what they really sometimes do on the crime shows. That would be something perfectly legitimate that they might find at a crime scene and say, okay, now what is this stuff? Of course, they have databases of specific varnishes. They could tell you exactly what it is. So you can get a lot of information here, is the point. You can get a lot of information, and you can go through one by one and figure out exactly what each one of those components were if you had enough time and enough energy to do that. Okay? So the important things about mass spectrometry, again, is you make the ions, you determine their masses, the molecular ions break apart, and so you get these fragmentations. We'll talk more in detail about the fragmentations next week and how you get them, because it's a good review of radicals and of carbocations and drawing resonance structures. And so as we go through that next week, it fits in well with lecture. And then if you wanted to determine what the molecule was, you have the ability, if not to nail it down exactly, but you can at least narrow down your list. And again, if you had authentic samples of all these and you knew what the retention times were, then that's what you would have them nailed down 100% of the time. And that's what happens in a forensic lab. Okay, and it's quick. It's a really easy technique. Put 10 samples on, they'll be done in a few hours. And so from the organic standpoint, you can get structural information and identity information. And from protein work, people do sequencing, and I'm not going to get into those techniques down the line. Right. So next week we'll talk more about fragmentation and the details of